today's session. Today we are going to discuss some short questions from time varying field. Myself, Dr. Sayanti Chatterjee, Associate Professor of Institute of Aeronautical Engineering College in EEE Department. So the first question comes, how the time varying fields are developed. Time varying fields are produced due to the accelerated charges or time varying currents. If the charges are accelerated and our current is time varying, then we can produce a time varying charge. You can see here, it is a time example. This green one is an, or the charges are accelerated. It is an example of time varying charge. A time-varying electric field is produced by the time-varying magnetic field. The blue one is the time-varying magnetic field. So we can tell that a time-varying electric field is produced by a time-varying magnetic field and vice versa. What is the meaning of vice versa? Time-varying magnetic field is produced by the similarly time-varying electric field. The first concept was experimentally induced by the Michael Faraday in the 17th century, and the second was theoretically introduced or mathematically introduced by James Clerk Maxwell. So Michael Faraday and James Clerk Maxwell are known as the father of the electrical engineering. So what is electromagnetic field? A field is a function that specifies the quantity everywhere in a region or a space. If there is a region or a space, a function that specifies a quantity everywhere in the region or the space. A field is a spatial distribution. A field is a spatial distribution of a quantity. It can be either scalar or vector in nature. If you can see that scalar field is the example of the scalar field is the heat or temperature. So it doesn't have in an area, if we keep something, we can feel the heat. So this is the field. And what is the vector field? Vector field is the electrostatic field, magnetic field. So because it has certain direction. So field is basically in the electromagnetic field. Field is basically three types: electric field, magnetic field, and electromagnetic field. The electric field is due to the static charge. Magnetic field is due to the permanent magnet. Or static electromagnet. And electromagnetic field is again two types. One is the time independent field, another one is the time varying field. So field can be divided into three parts: electric field, magnetic field, and electromagnetic field. Next, demonstrate the Faraday's law of electromagnetic induction in the vector form. We have to discuss the Faraday's law of electromagnetic induction in the vector form. So we know already what is the Faraday's law. Whenever there is a rate of change of flux, there is some induced EMF. The magnitude of the induced EMF is directly proportional to the rate of change of voltage. Number 3, which is known as the Lenz's law, that the direction of the electromotive force or EMF will be such that it will always oppose its cause. So direction with EMF will be such that it is in the opposite direction of the electromagnetic field. So if we want to draw the electromagnetic field induction, we can write that the EMF is, you can write in our EMF E is directly proportional to the minus of d phi by dt, or E is directly proportional to the d phi by dt, and E is equal to minus n d phi by dt. Now, if the number of turns is equal to 1, we can write E is equal to n d phi by dt. Actually, this is the Faraday's law in the scalar form. This is the Faraday's law in the scalar form. Now, if we want to move it into the vector form, what we will get? We know flux phi is nothing but the integration of B dot ds. What is B? B is nothing but the magnetic flux. What is then E? E is equal to d by dt integration of B dot ds. We got the value d by dt B dot ds. Again, what is EMF? EMF is actually in an open circuit, we call it EMF, but in a closed circuit, we call it voltage. And what is voltage? Voltage is nothing but the E dot dl. What is the meaning of E dot dl? E is capital E is nothing but the electric field intensity. So we can write, if we combine these two, E dot dl is equal to B dot ds. And what is E dot dl? E dot dl can be rewritten as grad cross E into ds. We are using the Stokes formula here, Stokes theorem here. By using the Stokes theorem, we can write grad cross E ds is equal to dB by dt into ds. So if we, and there is one minus sign because E is equal to minus d phi by dt. So if we combine these two equations, we will get grad cross E is equal to minus del B by del T. Grad cross E is equal to minus del B by del T. And this equation is known as the Faraday's law in the vector form. So we got the Faraday's law in the vector form. Now determine the expression for EMF induced in a coil. So in order to generate EMF induced in a coil is nothing but the dynamically induced EMF. So actually induced EMF can be classified into two parts. One is called the dynamically induced EMF and another one is the statically induced EMF. What is the dynamically induced EMF? In the dynamically induced EMF, the magnetic flux is fixed, but the coils are rotating. So when there is a rotating coil but flux is fixed, then we will call it a dynamically induced EMF. Like in generator motor, we got the dynamically induced EMF. But what is the statically induced EMF? Statically induced EMF means if the flux is moving but the coils are fixed. This is called the statically induced EMF. We can get it in the transformer. So what is the EMF? In order to generate a dynamically induced EMF, the magnetic field system must be kept stationary. As I told, magnetic flux or magnetic field system must be kept stationary while the coils of the conductors are moving. The coils of the conductors are moving, but the expression of the EMF is fixed. If the aforementioned process are always followed, the conductor cuts the magnetic field and EMF when there is a flux is fixed but the coil is rotating. So coil is rotating means there is a rate of change of flux, and as the Faraday's law, the EMF will induced. Therefore, the EMF can be written as the BVL sin theta. What is B? B is the flux density, B is the velocity, and what is L? L is the length of the coil. So we can determine the expression of the induced EMF. Just we have discussed in the previous question, same question here, types of EMF induced in the coil. So as I told, induced EMF, what is the induced EMF? According to the Faraday's law, if there is a rate of change of flux, there is a EMF, and this EMF is known as the induced EMF. Induced EMF is basically static, two types. One is statically, one is dynamically. What is statically? Conductors are stationary and the flux are variable. What is dynamically? Conductors are rotating and the flux is constant. So statically induced EMF. So the statically induced EMF is also known as the transformer EMF, and the dynamically induced EMF is also known as the motor, or generally known as the generated EMF. Next, so same question, the question may come like this: what is the dynamically induced EMF? So you can see this is a coil and we can move the magnet, so there is a rotating field. So the generation of the potential difference in a coil due to the change in magnetic flux is called the electromotive force. What is the electromotive force? The generation of the potential difference in a coil due to the change in magnetic flux. In order to generate dynamically EMF induced, the magnetic field is kept stationary and the conductors are moving. And the equation is BLB sin theta. So list out the Maxwell's equation in the static field. When we are thinking about the static field, we are thinking about the two equations. Actually, Maxwell's equation is the fourth Maxwell's equation. First one we will call the static Maxwell's equation. And another one is the static Maxwell's equations. And another one is the time varying magnetic Maxwell's equation. So static is again two types. Number one of the static equation is from the electrostatic. And for everything there are two forms. One is called the integral form. Another one is called the point form. So what is the integral form of the electrostatic? Electrostatic first point form is grad dot D is equal to rho V. We are getting it from the Gauss law. This is the modified Gauss law. What is the integral form? D dot D is, what is D? D is nothing but the electric flux density. D dot ds is nothing but the rho v into dv. Rho v is the volume charge. Number two is the for the electromagnetic, and this law is basically the Gauss law. Sorry, this is for the magnetostatic field. One is the electrostatic field, another one is the for the magnetostatic field. So it is the Gauss law in magnetic field. And what is the equation? Equation is the B dot ds surface integral is 0 or grad dot B equals to 0. So we can write these are the static fields in the integral. We have discussed the integral form as well as the point form. Same answer we can got for the time varying field. Time varying field is for one from the time varying electric field, and next one is the time varying magnetic field. So again it has two terms. One is the integral form and another one is the point form. Again we have two forms. One is the integral form, another one is the point form. What is the integral form of the electric field? Electric field first point form is grad cross E is equal to del B minus del B by del T. What is the integral form? Just we have discussed our previous lecture. E dot dl is equal to integration minus of integration del p del t into ds. So this is the electric field. If we move to the magnetic field, so first point form, what is the point form? Grad cross H, because H is a magnetic field intensity, is equal to J plus del D by del T. J is the, actually we got it from, this is the modified Faraday's law, as we discussed. This is the modified Faraday's law, and this is the modified Ampere circuital law. We got the modified circuital law. Grad cross H is equal to J del D by del T. Or we can write grad cross H. So we can also write like this. H dot dl is equal to J dot ds plus del D by del T into ds. So what is the del D by del T? Del D by del T is nothing but the leakage current or the displacement current density. So though the question is about the static field, but in this question we have discussed about the static Maxwell's equation and the time varying Maxwell's equation is both integral form as well as the derivative form or point form. Next question is, what is displacement current? When just we discussed in the previous slide, you can remember grad cross H is equal to J plus del D by del T. And I told that time that the del D by del T is nothing but the displacement current. Now the problem comes, what is the meaning of the displacement current? What is displacement current actually? When current is flowing through a conductor, there is some extra current which goes in the dielectric, which can be known as the leakage current or displacement current. So here we will discuss about the displacement current. So we know in a capacitor the current IC is equal to C dV by dt, and this amount of current is only going through the capacitor. So what is the capacitance of the capacitor? Capacitance of the capacitor C equals to epsilon A by D. So what is the value of the IC? IC is equal to epsilon A by D into, what is the value of IC? C epsilon A by D dV by dt. Now epsilon A by D dV by dt. So we can write here epsilon dE by dt, because dV by d, we know that the EMF is equal to, again intensity is equal to voltage or potential gradient. So E is equal to dV by d. dV by d is nothing but the E. So we got epsilon IC by A is equal to epsilon dV by d is nothing but the dE by dt. Again epsilon dE nothing but the d by d, because the d is equal to epsilon into E, and we got the displacement current JC is equal to d by dt. So this is the current density we got from the previous equation, and in the modified Ampere's law, grad cross H is equal to J, we can prove from the Ampere's law, but that is only the conduction current. But in the practical case, current is there in the displacement current also. So this is known as the displacement current density. So while we are discussing the displacement current density, another problem will come. What is the conduction current density or conductor current density? Conduction current density refers to the amount of the current flowing through the flowing on the surface of the conductor in a time t. So what is the conduction current? Conduction current density refers to the amount of current flowing on the surface of the conductor or conduction band in a time t. If there is a voltage source connected to one capacitor, there are some resistor is there. So the current flowing has the two value. One is coming to the resistor and another is a very small amount which is going in the medium or the dielectric, and this amount of current is known as the displacement current. So I has two part, IR, current through the resistors and current through the capacitance, or we can write I is equal to IR plus IC. We can write I is equal to IR plus IC. Now if we divide the two sides by A, we will get I by A equals to IR by A plus IG by A, or we can write J by JR plus JC, or JR is the conduction current density and JC is the displacement current density. So already we have discussed the Maxwell's equation in the time varying field, and there is in the time varying field we can also modify the equation. We already got E is equal to E naught cos omega t. So similarly we can write it E naught j omega t. So we can also write E and D. The relation is D is equal to epsilon E, and epsilon is a constant. So the nature of the D will be same. So D is equal to D naught e to the power j omega t. So we have to get the dd by dt. So what is the dd by dt? D naught omega j e to the power j omega t. So the maximum value is j omega d naught. We got the maximum value j omega d naught. So if we compare the equation, we got dB by dt is equal to j omega b. So grad cross E is equal to del B by del T is equal to j omega b. This is the modified Maxwell's equation in the time varying field. Similarly, we can get grad cross E is equal to j omega mu h. It is the time varying equation for a magnetic field. State the Faraday's law of electromagnetic induction. Any change in the magnetic field of a coil of wire will cause an EMF to be induced in the coil. This EMF induced is called as the induced EMF, and if the conductor circuit is closed, the current will also circulate through the circuit, and this current is known as the induced current. So how we can induce the current? By moving the magnet towards and away from the coil, by moving the coil into or out of the magnetic field, by changing the area of a coil placed in the magnetic field, and the fourth one is by rotating the coil relative to the magnets. What the Faraday's law states? Faraday's law states that the magnitude of EMF induced in the coil is equal to the rate of change of flux, and that linkage with the coil, we can also write that the E is equal to minus d phi by d. What is the Maxwell's law in a glance? Maxwell's law in a glance can be written as grad cross E is equal to minus del B by del T, and E dot dl is equal to minus S del B by del T into ds. Grad cross H is equal to J plus del D by del T. Again H dot dl. So these are for the time varying field, and this too is for the electrostatic field. Now next question is, write the Maxwell's equation in the free space. So for the free space, we can assume that the current density equals to 0, and the volume charge distribution rho or rho b is equal to 0. Permittivity F is equal to epsilon and mu is equal to mu naught. So we first law we know grad dot d is equal to rho v. So grad dot epsilon E is equal to rho v. So grad dot E is equal to rho v by epsilon. This is the general thing. But in the in the free space, we always take some assumptions that the current density equals to 0. Current is equals to 0 means there is no charge, and there is no charge means rho b equals to 0. So grad dot E is equal to rho b into epsilon. So if there is no charge, so we can write grad dot E is equal to 0. From the second equation already we got grad dot B is equal to 0. Grad cross E is equal to minus del V by del T, Faraday's law, and grad cross H is equal to J is the Ampere circuital law. As there is no current, so current density will be 0, and we can write grad cross H is equal to 0. So if we want to modify it for the free space, we can write grad cross H is equal to del D by del T. Grad cross H is equal to del D by del T. So this is the modified form for the free space. What is skin effect? Skin effect is one phenomena of the electric lines which arising due to the unequal distribution of the current over the entire cross section of the field, being used for the long distance. So what is skin effect? The phenomena arising due to unequal distribution of the current over the entire cross section of the conductor being used for a long distance power transmission is referred as the skin effect in the transmission line. Such phenomena does not have much role in play in the case of the short lines. It is only effective for the long lines only. The distribution of current over the entire cross section of the conductor is quite uniform in case of the DC system, but we are using the present era of the power system engineering is predominantly an alternating current system, and here the AC current will increase the skin effect, means the resistivity or the impedance of the conductor, and this is called the skin effect. What is Poynting theorem? Poynting theorem states that the rate of energy transfer per unit volume from a region of space equal to the rate of work done on the charge distribution in the region plus the energy leaving the region. We can write it as the P. The Poynting theorem is known as the Poynting vector, named after the John Henry Poynting, is used in order to demonstrate the energy flux density of the EM field. As per the definition, Poynting vector is the result of the vector product of the field current and the magnetic components. So what is this? P is equal to E cross H. What is E is the electric field intensity and H is the magnetic field intensity. Show the expression of the induced EMF of the Faraday's disk generator. Again, Faraday's disk generator is nothing but the induced dynamically induced EMF, and the equation is again BLV sin theta. The dynamically induced EMF can be written as the BLV sin theta. Okay. Find the expression for the wave equation. While we are thinking about the wave equation, first we will discuss about the free space. The wave equation of the free space. So what is the wave equation in the free space? We know that we will use the two equation, grad cross E is equal to minus del B by del T, and we will use the another equation, grad cross H is nothing but the del D by del T. So if we equate these two equations, we can get the equation of the wave equation. Actually, what is the electromagnetic wave? Electromagnetic wave is an oscillating wave when the electric wave and magnetic wave are superimposed on each other. And what will happen if this is an electric wave? If this is an electric wave and we have another magnetic wave with us, So if they superimpose, they will create a new wave, and this wave is nothing but the wave equation. So we can do from these two equations combined together and we get the wave equation in the free space. Wave equation we can write in terms of the electrostatic field, or we can write as the magnetostatic field. Electrostatic field intensity and magnetostatic field intensity. So what we got? Grad square E is equal to mu naught epsilon naught d square E by dt square. Again, 1 by root of mu naught epsilon naught is 1 by mu naught epsilon naught is nothing but the C. 1 by square root of mu naught epsilon naught is nothing but the C. So what is C? C is equal to the velocity or the speed of light is equal to 3 into 10 to the power 8 meter per second. So we can write it like this. This equation can be rewritten as the grad square E minus 1 by C square d square E by dt square is equal to 0. So this is basically the wave equation, or we can write from the electromagnetic field grad square H minus 1 by C square d square H by dt square is equal to 0. We can write the wave equation in the both term. We can use the equation. The details derivation has already discussed in the previous discussion. What is the wave equation in the case of the conductor? So already we got grad square E is equal to epsilon del square E by del T square mu into E, because in the case of the conductor there you cannot write mu is equal to mu naught and epsilon is equal to epsilon naught. We cannot write the equation. Rather we can write grad square E is equal to mu epsilon del square E by del T square E by del T square. We got it from the previous expression, plus mu delta del E by del T. Mu delta is equal to del E by del T. What is this? Sigma. Sigma is nothing but the conductivity of the metal. So this is the wave equation in the conductor. Next we will discuss about the wave equation in the insulator. Maxwell's equations are modified for epsilon r and mu r. So we can put the D is instead of epsilon naught E, we can write epsilon r epsilon naught E, and B can be modified as, except we wrote previously mu naught H, so it will be mu r mu naught H. So what is the grad square E? Grad square E is the epsilon r epsilon naught relative permittivity but mu r mu naught. So already we know epsilon naught mu naught is equal to 1 by C square. So we got the equation grad square E minus epsilon r mu r by C square del square E by del T square is equal to 0. So this is basically the wave equation for an insulator. What is V? V is the wave velocity is equal to 1 by epsilon r epsilon naught mu r and mu naught. Already we discussed in the last slide 1 by mu naught and epsilon naught. If we put the value, we will get the value of the C. Why? Because if we put the value mu naught is equal to 4 pi into 10 to the power minus 7 and epsilon naught is equal to 8.854 into 10 to the power minus 12. If we put the value, we will get the value of the C, and C is nothing but the speed of the light. So today's discussion we have discussed about some important short questions of the time varying field, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.